Recording started.
Okay, welcome to part 2 of lecture 2. What this is now is where I'm going to show you how to code the dynamics and the kinematics in MATLAB Simulink. I've opened MATLAB, I've created a folder called AE4901, blah, blah, blah. So then I'm going to open, what you'll see here is I have many different versions of the simulation we're going to create. And this one's called my latest and greatest, my working file. In this working file, let me shrink MATLAB so we can look at latest and greatest. What you'll see is I have open a scope of the Euler angles. We're going to concentrate on this block today called dynamics. I've previously introduced, we will command, sum, turn, roll, pitch, or yaw. I'll teach you how to generate a good trajectory, a realizable trajectory to accomplish that command. That will be sent to a controller that if you wanted to achieve this command, there's a certain torque signal required, and the controller will calculate that torque signal. That required torque signal will be sent to an actuator, which produces that control torque. The control torque we can create, but the disturbance torque we can't. But they are nonetheless summed, and they both act upon the dynamics, which are nothing more than, it's a slang term, dynamics, but it's the governing differential equation of motion. We've seen that it is also Newton-Euler's law is another name for rotational differential equation of motion. And we saw alternative or Lagrangian mechanics way of investigating as well. So in this block dynamics, we're going to find if you apply this torque, a control torque and disturbance, a torque is like a acceleration, just like a force, like an acceleration. The torque is like an angular acceleration. So we'll apply some angular acceleration to the spacecraft, and that will result in some rotation of Euler angles. And I'll hit run so you can see this program right now is at 5 seconds going to execute a 30-degree yaw command. Roll and pitch, don't move. It will be accomplished by 10 seconds, and then it will regulate at 0. Don't mind all these plots for now. I'll explain some about it in just a little bit. So we're outputting these Euler angles because it's easy for me to look at this and understand. Got it. 30 degrees, yaw, no problem. Now look, green, agua, oh, that's yaw, okay. Yellow and pink are roll and pitch, so I understand. Note how I'm writing right in the field so I can understand what's going on. T disturbance, all of that. I double click in the field, type a bunch of stuff. You could right click the box and change the font, make it much bigger if you want. So then later you can come back and have annotations about what's going on. Like any class, you can come back sometimes later and read your own computer code and think, what the heck was I doing here? So it helps to type right in the field. So we're going to use dynamics block today, where the disturbance and control torque come in as applying an angular acceleration to the dynamics. It will result in some rotation. This is the solution to the governing differential equation of motion. What's your state, your roll, pitch, yaw, position state, or angular position state? But we're also going to output a direction cosine matrix in order to calculate our disturbances. Our direction cosine matrix references our position of the spacecraft's attitude relative to the orbit frame, and that is more relevant to figure out how much gravity gradient, how much solar aerodynamic torques, and all of that that we'll talk about next week. So in addition to just doing the dynamics inside this dynamics block, we're going to have a kinematics block where we calculate this direction cosine matrix. We're going to output the Euler angles just for display. Then I'm going to mux together our position with our rotational rate to form what's called a full state feedback. So we'll have the state x and the state x dot. And we'll put them together to call that full state feedback. And that will be something that's actually occurring